So I'm going to stand up here with my exoplanet hat on. I have lots of hats. There's a joke about that. But I actually am a card-carrying planetary scientist. I did my PhD actually on the lower atmosphere of Venus. I was one of the first people to look through the near-infrared windows all the way down to the surface and map it. And I used that opportunity to try and map water vapor in the lower atmosphere. I also looked up in the mesosphere to track oxygen air glow from oxygen singlet delta to understand mesospheric dynamics and patterns, or at least to show that that's a mechanism that we could do that. And so the joke is that I must love a challenge because I tried to look for oxygen and water vapor on what is arguably the least habitable planet in the solar system. Okay, but it was good training for what was about to come. Now I work primarily in modeling of extrasolar terrestrial planets, but the good news is that photons are coming, and with JWST and ground-based telescopes that are planned, we're going to start actually getting data on these things. So I'm up here representing the sort of ExoPAG part of this joint PAG activity, and so that's a community-based group that solicits and coordinates community analysis and input for the exoplanet exploration program. We organize study analysis groups and science interest groups, and I'll talk a little bit about one of those things later. We produce finding of analyses for the NASA astrophysics directors, that's Paul Hertz, and we make them publicly available to the community. And we're there to basically enable direct communication between the community and NASA, and also within the community itself, whenever issues come up that we'd like to address as a community. It's open to all interested scientists, and our next meetings are in July and January. I don't have the exact dates now, but that's typically when we meet. And the most important thing relevant to this group is that we're currently proposing to initiate a new science interest group on exoplanet solar system synergies. And that will be open to all members of the community. We really encourage cross-PAG interaction in this as well, so it's not just for ExoPAG folks. But we want to provide opportunities for ongoing discussions of exo and solar systems. So this conference is an example of the sort of thing we'd like to do, and explore how exoplanet and solar system missions can in fact benefit from each other. And I know Kathy is a very big proponent of that as well. So that's kind of where we're coming from. But first, I've got a fun issue here, but anyway, first I'm going to start with essentially a discussion of exoplanets for planetary scientists. I want to tell you a little bit about our triumphs, our limitations, sort of our goals and objectives, and what our future plans might be for exoplanets, with a view to trying to be empathetic towards what a solar system person might like. Now, even though Stephen told you that our image of a terrestrial exoplanet didn't look so great, we do have this. These are giant planets in the outer regions of their solar system, planetary system. And I love this movie because finally, after all these years, it proves to me that exoplanets are in fact real. They do move. They're not just stellar phenomena. We were always worried about that. Believe me, every exoplanet scientist was secretly worried that that's what was going on. But no, they are in fact real, and we can see them move. We also have loads and loads of them. So Kepler went out and found us a zillion planets, actually over 4,000. Are now confirmed and known. And the big surprise was the vast majority of the planets that were at least, that Kepler was at least sensitive to, are between the size of Earth and Neptune. We do not have an analog for that in our solar system. So it turns out at least the most popular planet that could be detected there is something we don't have any access to. So that already tells you something about the advantages of looking at the exoplanet system. It gives us more diversity. So you can talk about the solar system planets serving as exoplanet analogs, and this is the diagram here of the semi-major axis, the distance from the star, and the planet radius in Earth radii. So again, the theme of this conference is exoplanets in our backyard. You consider these planets to basically give us insights, because they're up close and personal. They can provide insights into environments and processes for some of the most common types of exoplanets, even though, as it turns out, we don't have any real direct analogs for these planets yet, but that data is coming. And so as Stephen pointed out, we are getting to the point where we really need to have these two communities get together. So the exoplanet population, to complement the detail we can get from the solar system, provides us with a lot of statistics on planets that we don't have in our planetary system. But as I said, there's no significant overlap at the moment between these sorts of diagrams. But this is helping to put our solar system in context overall. But I think this is quite a startling thing to know, that even though we have 4,000 planets, we're not quite getting to solar system analog situations yet. However, we can push forward with getting data on this to answer the fundamental question, are we weird? To which the answer appears to be yes. But you knew that. Jupiters may, in fact, be rare. And so some of the initial results coming out of the exoplanet statistics are that Jupiters are rare, with only about 10% of solar-type stars and 3% of M-dwarfs harboring giants inside of 10 AU. However, that estimate has been made on an extrapolation from the stuff we have closer in. And so we're hoping with the launch of WFIRST in about 2025-ish, 2026, I can't remember the exact date, we will have microlensing observations that will get us into that region where the solar system planets are and allow us to get more statistics on what is actually out there. WFIRST microlensing, though, does have some limitations. Typically only detects one planet in the system, so it can't give us an entire planetary system where we can see all of the different planets together. To do that, we're going to need large space-based direct imaging in the future. And that's something that's currently under consideration by the decadal. Okay, now, we're weird because we have a Jupiter. Jupiters turn out to be really important, and that's what we've been learning from our own solar system and also as well from exoplanet modeling, is that, you know, a Jupiter in your system, even if it just sits there, can be very important for basically the delivery of volatiles to forming planets. And if it doesn't just sit there and it moves, which is probably one of the biggest discoveries we've got out of exoplanet science, was just the prevalence of migration as a process, which in fact in turn caused us to look back at our own planetary system and come up with things like the Grand TAC model, where Jupiter and Saturn migrate in and then back out again, which actually explains the distribution and composition of asteroids in the asteroid belt. But the point is that with a Jupiter in your system, your volatile delivery is very different than if that is not the case. And so this is very interesting also in sort of the bigger picture context is, you know, did we have a Jupiter? Did that help us get volatiles to our inner planetary system? So the other sort of big surprise, as I said, were these sub-Neptunes, as they're called. So they're smaller than Neptune, but about and bigger than Earth. That class, it was an enormous blob until fairly recently, when it was very exciting to actually have improved size measurements that showed that huge blob of planets you saw there, the yellow swarm, in fact breaks down into two separate communities of planets. Some that appear to be what we call mini Neptunes. So they're smaller than Neptune. You can see Neptune would be around about here-ish. So the vast majority of these are smaller than Neptune, but appear to have comparable densities. So mini Neptunes, or I've been calling them Neptinis. And the terrestrial type planets here. So this is very exciting, is the planets that have a radius less than about 1.6 or 1.5 Earth radii appear to be probabilistically more likely to be of the same density or similar density to planets like the Earth and Venus. So this Fulton gap that has been discovered here, the interesting thing is that this is likely due to photoevaporation. That's the current ongoing theory for that. And if that is the case, then it may mean that in many of these planetary systems, these so-called terrestrials are actually essentially evaporated cores from things that may have had a much denser envelope. And so it may be that there are separate ways of making terrestrial planets to the ones that are in our planetary system. So the other, I think, astonishing thing that should be relevant to solar system scientists is that Neptune-mass planets, that big agglomeration of the Neptunes and bigger, show an astonishing diversity of densities. This is sort of 3 orders of magnitude in density for things that are that size. And these in particular, I've plotted things that are not highly irradiated. So this isn't puffiness per se. These are cooler things. You can see the sort of temperature here. This is cool for an exoplanet scientist, right? 800 Kelvin. But these things are, not, several thousand Kelvin, because we do have planets at that level. So wow, what's going on there? You thought Neptune and Uranus were diverse, but it turns out that things that are of a similar size in the exoplanet population just have a massive range of densities. So that's a question, is that due to formation history, thermochemical evolution, other processes, what's going on there? And maybe studies of Neptune and Uranus can help us get a handle on why those two objects are different and maybe help us understand what's going on with this amazing diversity. So yeah, so an improved understanding of solar system planet interiors is going to be very, very important to help us try and figure out these amazing phenomena and trends that we're seeing in the exoplanet population. Okay, I do want to point out, though, we do have multi-planet systems in the exoplanet population, but they're not our multi-planet systems. So the multi-planet systems that we typically have, which are found using the transit technique, which is very sensitive to planets close to the star, not surprisingly, finds multi-planet systems that are very close to the star, most of them actually within the equivalent of the orbit of Mercury in our system. And so we do have these, But again, we're not yet overlapping with true solar system type analog systems. And these close-in planetary systems are more susceptible to gravitational heating, gravitational tidal heating, and also to atmospheric loss and so on. So again, very different types of architectures, but we can learn a lot potentially from the processes that are going on in there. So I'm going to talk a little bit now about what we might be able to get in characterization as we move forward. And I'll point out that there are many, many ways to observe an exoplanet. A lot of this is really just stars behaving badly. We look at stars and we see how they're anomalous in some way. They're dimming, they're brightening, they're doing something. We are getting into the regime where in the future we hope to be able to do things more like direct imaging, which is probably more like the remote sensing in the planetary system, of course, though with not the same spatial resolution. But there are a bunch of techniques that we actually use to do this. So transiting planets are going to dominate our near-term observations for exoplanets, and these are essentially the three sort of major techniques that we would have for that. There's transit spectroscopy, where we pass directly in front of the star. Secondary eclipse, where we pass behind and we look at the emission before and during the pass behind the star, and we can separate out the planet there. We can also look at phase curves to just look at the temperature of the planet as it goes around in its orbit. And so these are the three techniques we're going to try and use to do these characterizations. But for those of you who know what a planet looks like, you realize this is going to be a challenge. All right, if we're trying to do transmission spectra and look at the atmosphere backlit by the star, we have what I call the tyranny of the thin blue line. I mean, we really are, as I talk to you about our future planned observations, just remember that's what we're trying to do. We're trying to look at essentially, a high molecular weight atmosphere, this very thin ring around the planet, be able to distinguish that as the starlight passes through it. So to do that, we're really going to focus on M dwarfs, planets that orbit M dwarfs, simply because the area of that thin, tiny ring is going to be much larger compared to the size of an M dwarf than it would be compared to the size of a G dwarf. And so because of that, the anomalies in the drop in radiation as the light passes through the atmosphere are relatively larger, and so we have a better chance of seeing them. So M dwarf observations are the way to go in the future, and our star system here is the TRAPPIST-1 planetary system, which Stephen mentioned as well. So you should know that name if you know no other planetary system for terrestrial planet characterization. This one, TRAPPIST-1, is an M8 dwarf, and a very, very cool M dwarf, barely above the brown dwarf sequence, and it's tiny. It's barely bigger than Jupiter, and it has 7 roughly Earth-sized planets orbiting around it. And because of the ratio of that tiny star, that Jupiter-sized star, to the Earth-like planets, we can get good spectral signal through it. Going back to the Jovians, though, so we've used these techniques as transmission technique on hot Jupiters. Hey, it's a hot Jupiter. It's a Jupiter that's massively inflated. How different could they be? It turns out when we do systematic surveys, like this fantastic one led by David Singh, what we see is a huge diversity in spectra, showing a diversity of different types of clear and cloudy atmospheres, strong stratospheric temperature inversions or not, and a different range of abundances, which the exoplanet people call metallicities. And this is because of Stephen's point. Remember, exoplanet science is really stellar astronomy. And so I have finally come to the realization in the last year that the reason that exoplanet scientists use metallicity is because they actually think planets are just tiny stars. Okay, and so they've been able to work, they've gotten away with it because they're hydrogen-dominated planets so far, okay, but pretty much soon they're going to hit the terrestrials, and that is just not going to work anymore, right? So when you see metallicities, exoplanet astronomers are saying, hey, 1 solar metallicity is 1 unit. If this thing has 30 times solar metallicity, it's 30 times metallicity. So that's what they're talking about. But that is a stellar term. And so you can tell where they're coming from. Okay, for exo-Neptunes, we've also got a suite of spectra, about 6 at the moment. What we're seeing there is a diversity in potentially water vapor as a function of temperature. So we see that happen. But if you look at the sort of planets of different sizes and plot them along this metallicity versus mass curve, you can see that we are sort of roughly following the sort of metallicity. So metallicity, what that means is really just a fraction of things in the planet that are heavier than hydrogen and helium. So what they're seeing is an enrichment versus a hydrogen-helium fraction as you go towards smaller planets. Okay, and then I think the most important and exciting thing right now for exoplanets is that we stand on the brink of exoterrestrial characterization. So we have now gotten to the point where people are actually giving us observing time on major telescopes to try and get spectra of terrestrial exoplanets. So these, I think, are some of the more exciting observations, and they show, by the way, absolutely nothing significant. However, that does help constrain quite a bit. So, so here we have observations of the TRAPPIST-1 planets taken with HST. They essentially show a straight line, no signal there, but what they do is they rule out a hydrogen-dominated atmosphere, both clear from the data, and then there's been some very clever work done by people in Sarah Hurst's lab, Sarah Moran, looked at, sort of aerosols that would need to block radiation up high, and then looked at theoretically whether they would be suspended in the atmosphere and showed they wouldn't be. So essentially the data and the lab and theory rule out both clear and cloudy hydrogen-dominated atmospheres for these planets, leaving us with the exciting conclusion that they're probably high molecular weight atmospheres like our Earth. So, or there's no atmosphere at all. Those are the two options, right? So, and then over here, work done by Del Rez et al., not statistically significant yet, given these are 1 sigma error bars. But if this disparity holds, these are Spitzer observations. Of course, we have said goodbye to Spitzer a few days ago. But if we can get similar observations like this with JWST, that might actually hint at carbon dioxide in the atmosphere of this planet, which would place it as squarely a terrestrial type of atmosphere. All right, so the other thing you need to know is the very first planets we're going to try to observe with JWST will be Venus's sisters. They will be highly irradiated terrestrials. Sorry, when we're talking about terrestrials, people will go after a bunch of Jovians and Neptunes, but if we're pushing down to the terrestrials, the first one we will try to observe will be the ones close to the star. So in this case, probably TRAPPIST-1, B, and C, and so, and GJ1132b. So that's super exciting, and Laura's going to talk, I think, more about these probably in her talk as well on interiors. But that is definitely where we're going to go. So I think understanding Venus will help us to interpret some of the very first terrestrial exoplanet data that comes back from these. And yes, I always like to make the joke that Venus is actually the popcorn of the solar system, if you consider Earth to be a kernel of corn, because Venus has gone through this evolutionary sequence, which leads to my next point, which is it'd be very interesting to see if these planets that are highly irradiated that are very close to the star have undergone the same process as Venus, and whether we see CO2-dominated atmospheres with them. And so that's the point in this one here, is that we have Earth and Venus around the sun, which is a G-dwarf. A G-dwarf is relatively well behaved as it evolves. So when it's shortly after it's born, and this is its evolution in factors of 10 to 10 gigayears, a G-dwarf starts off a little bit bright, and then eventually starts to brighten up through this sequence here. And what you're seeing here is actually the edge of the habitable zone, just showing how much it would evolve. Interestingly, around an M-dwarf, and especially the late type M-dwarfs that we're going to be looking at initially because we get better signals, there is a massive brightening early on. It's called the superluminous pre-main sequence phase. And what that means is that any planet that forms in what is now the habitable zone, as you see it, has been subjected to massive amounts of luminosity, of brightness early on, which probably would drive a runaway greenhouse type effect on anything that looked like a terrestrial planet. And so these planets around M-dwarf stars may come to us, factory pre-installed heavy carbon dioxide atmosphere. But unlike the Earth, where our star just continues to brighten, these planets will start out very bright, go through the runaway greenhouse, and then the star will dim. We don't know what happens when that happens, right? So that is going to be a very interesting comparative planetology on the evolution of terrestrial planets. The other thing I want to point out is if that evolution changes the composition, it then also potentially changes the temperature of that planet in the habitable zone. This is running essentially what the surface temperature of a habitable zone planet would be if it had a bunch of different types of atmospheres that are the outcome of that early evolution. So that early evolution could drive runaway greenhouse into a Venus-type atmosphere, or it could drive lots of an ocean into a heavy O2 atmosphere if you overwhelm the sinks for O2 in the environment. So this will be fun to go look at the TRAPPIST-1 system, see whether or not they actually have these types of atmospheres from evolution, or whether in fact they are habitable in the habitable zone, which might happen for a bunch of different reasons. The interesting thing, and the reason that might happen, is the TRAPPIST-1 system. If you look at the densities of the planets in this system, they are nearly terrestrial, but they are on the side of a higher volatile content, which is likely due to their formation further out in the system and then migrating in. And so these could be very different types of terrestrials to the ones we're used to, that relatively high volatile content. The current sort of estimates look at about maybe 5% water by weight for these types of planets. Okay, and I think the main message I'm going to say here is that multiple groups now have shown that a high molecular weight atmosphere on these planets may be detected in as little as sort of 2 to 6 to 10 transits with JWST. And that is looking for signatures primarily from carbon dioxide in the atmosphere. So it is not impossible that we will, in fact, be able to tell whether or not these planets do have terrestrial atmospheres. Detecting what's in them is going to be more challenging, but there's things that we can certainly go after. If we want to look for loss of an ocean, we could go after O2 collisionally induced absorption in the atmosphere, which would occur if we had a multiple bar oxygen atmosphere. We can also go after CO2. Water vapor, ironically, is much more challenging, and that's because if this is a habitable planet, it will have a cold trap. The water will be kept down near the surface, and transmission tends to go through the sort of upper troposphere and up into the stratosphere, which can be quite dry on these planets. So, but nonetheless, we're going to go try and look for those sorts of things. Oxygen is unlikely with JWST for TRAPPIST-1. The features are very small relative to these other features. The methane and CO2 features will dominate. Thomas Fauché, who is here, I believe, also came up with this idea of looking for O2, and O2N2 at 6 microns. But if I read your paper correctly, Thomas, you also say that's very difficult for TRAPPIST-1, and it's much better for planets within 7 parsecs, right? Would be the ideal. So maybe not for TRAPPIST-1, looking for that particular mechanism. There's just another group that's just shown how difficult it will be to get oxygen. All right. So we may not be able to do oxygen from JWST, but ground-based telescopes are coming online, extremely large telescopes, ELTs, 30 to 40 meters in diameter. Can't wait for those to get online. They will have ultra-high resolution spectrographs on board that can potentially separate out the reflected light or the transmitted light from a terrestrial-type planet orbiting a star and look for oxygen, 0.76 micron, 1.27 micron oxygen bands in their atmospheres. Okay, so very, very quickly, things we need, observing the solar system, we need fundamental things that you planetary scientists are probably going to say, well, that's pointless. Why would you need that? We need things like actual albedo, looking at all the physics in an atmosphere, all of that scattering. Can you tell us the albedo as a function of phase for these planets? And so Laura Mayoga, I think, is also going to talk about this for Galilean satellites later, so you can see her talk. We need observations of occultations, observations where there's some backlit source going through an atmosphere so we can simulate what a transmitted spectrum might look like. We need to understand how secondary atmospheres are generated and maintained, atmospheric loss and outgassing. We need to understand the chemistry of some of these planets. For example, Venus may have lost an ocean early on. Did it have an oxygen-dominated atmosphere at that time? Did it lose it? Why don't we see oxygen being produced on this planet at this time? And that's important for us understanding false positives for biosignatures like oxygen. So I will finish up there just with my summary, but I just want to say that, you know, one day I hope there won't be just exoplanet scientists and solar system scientists, but there'll just be planetary scientists, because that's what we're studying.